Okay, this is video 3 for the energy and power unit notes. In this one, we're going to talk about conservation of energy. Now, in the previous video, I mentioned something called a conservative force. A conservative force is a force that returns a system to its equilibrium. So gravity is a conservative force because it brings the system back to, if you lift something up, it brings the object back down to the ground. Elastic forces are conservative because when you pull on a spring, the elastic force returns it to where its original length was. Friction, however, is non-conservative. Friction will not return a system to its original state. So friction is non-conservative. Well, conservative forces then allow us to have conservation of energy. So the forces that are responsible for that form of energy, like gravitational force with gravitational energy and elastic forces with elastic energy, those allow us to have conservative forces, and we have conservation of energy because of that. So what conservation of energy says, energy cannot be created or destroyed. However, it can be converted from one form into another. And again, this is only for conservative forces. So friction, again, friction steals energy from the system. Now this leads us to something called mechanical energy. Mechanical energy is equal to all forms of kinetic plus all forms of potential energy. And as long as we have conservative forces in a system, mechanical energy will be conserved. So let's take a look at a couple examples then. In this first one, we have a boy who's sliding down a ramp. Now, the force acting on this boy then is just going to be a gravitational force. And gravitational forces are conservative, so that means the energy in the system will be constant. Now, I know there's a little bit of friction between the wheels and the ramp, but that's so small we can ignore that. All right, so what we want to do is we want to find out how much energy is in this system, and we're given some clues here. So we're given a clue there, we're given a clue here. So here I see I have some mass and some velocity, so that means I can go ahead and calculate the kinetic energy. And doing that, I find that the kinetic energy is going to be 1,920 joules. Now, at the ground here, my delta Y equals 0. So for gravitational potential energy near the Earth's surface, I see that because the young man's at the surface, there is 0 joules of potential energy. All right, well, mechanical energy is the sum of kinetic and potential. So that means that this mechanical energy then is 1,920 joules. And that means that that's how much energy this system has. So everywhere I see mechanical energy, I know that it's going to have the same amount. All right. At the very top up here then, I'm going to go ahead and say that there's 0 meters per second of energy, or meters per second of velocity. So what that means is I'm going to have no kinetic energy, 1,920 joules of potential energy. So to get the height, or my delta Y, I can just take the energy and divide it by mg, because I know the mass of the boy is 60, g is 10, so that gives me 3.2 meters. All right, now for the middle one, I know the height here is 1, so I can go ahead and calculate that, and I find that I've got 600 joules of potential energy, and that should be pretty easy because it's 60 kilograms times 10 times 1. So doing a quick subtraction here, that kinetic energy then would equal the mechanical energy minus the potential energy, I see that I have 1,320 joules of kinetic energy, and then the velocity, let's see, it'd be 2 times the kinetic energy divided by mass, in order to take the square root, and I would get about 6.6 meters per second. So that's just using some logic to go through this one. All right, let's take a look at another example. Here we have a bicycle wheel that's been placed on a ramp. The ramp is 2 meters tall, 7 meters long. And I want to know how long, so that's a time question. How long will it take the wheel to reach the bottom of this ramp? All right, to answer this one, I'm going to use conservation of energy. I'm going to say that the initial mechanical energy must equal the final mechanical energy. So all the energy at the start must equal all the energy at the bottom. So mechanical energy is all forms of kinetic plus all forms of potential. So I've got some linear kinetic plus some rotational kinetic in the initial values, plus some initial gravitational potential energy, and that equals the same, kinetic and potential at the bottom of the ramp. Now, I can do some canceling. I'm going to say that this starts off at rest. So the initial velocity equals 0. So that means that this term's gone, this term's gone. I'm going to say at the bottom of the ramp, it's used up all of its potential energy, so there's no more gravitational potential energy at the bottom of the ramp. So what I'm left with is gravitational potential energy and then linear kinetic energy and rotational kinetic energy. Okay, a bicycle wheel is a ring, so the moment of inertia of a ring, we want to remember, is mr squared, where r is the radius of the ring. Also, we have our bridge between linear and rotational, v equals r times omega. So doing some substitutions, I can do that. We can now do some canceling. All of the mass cancels. And for this, I'm going to get an r squared canceling up here. So what I'm left with is this expression right here. So basically, the velocity at the bottom of the ramp will equal g times y, square root. So the velocity at the bottom of the ramp will be 4.47 meters per second. All right, let's go ahead and use that then. Okay, so I know that my x initial is 0, x final is 7 meters, and final velocity is 4.47 meters per second. I don't know the acceleration. Okay, from this I can use some kinematics equations. I can use this expression to get the acceleration. And then, to finish it up, to get the time, I can use this expression. And I find that the time it takes is roughly 3.13 seconds. All right, let's look at one more problem. Escape velocity. So I want to use conservation of energy to derive a formula which will allow us to calculate the escape velocity of a planet. As we all know, if you throw something up, it's going to fall back down. If I give it a greater velocity, it's going to go farther and fall back down. But there is one velocity that if I throw it at that velocity, it's fast enough where it will not fall back down. It will escape the Earth and never return. And we want to be able to calculate that. So here's a couple of things for the setup. So let's say here's our Earth, and we want to give something an initial velocity so that it goes away to a point infinitely far away. Now, as this thing goes away from the Earth, it's going to slow down, so that at infinity, its final velocity will be 0. Also, potential energy will decrease as well. Gravitational potential energy is equal to this formula here. And notice that as r becomes larger, the energy becomes smaller. So at infinity, we have no gravitational potential energy as well. So here's what we have. The initial mechanical energy must equal the final mechanical energy. So we have this initial kinetic energy plus some initial gravitational potential energy equals final kinetic plus final gravitational. But at infinity, the kinetic energy goes away, and so does the potential energy. So what I'm left with then is 1/2 v naught squared plus You may be wondering why I'm using the radius of the Earth. Well, that's because initially the object is resting on the Earth's surface. So initially the value of r is going to be the radius of the Earth. There's a negative because, it's a bound system. So now we can do some algebra. We can do some canceling. It doesn't matter how massive our spacecraft or rock or person is. And we find that the escape velocity can be found with this expression here. For Earth, it's right around 11,000 meters per second. It's 24,500 miles per hour. So if you were to take a rock and throw it at 24,500 miles per hour, that rock will escape the Earth and never return. All right, this concludes our video 3 for energy and power.